Hi, this is Austin. This is Lab 3 for Kinematics and Dynamics, and Lab 3 is going to be a Scara Arm. So a Scara Arm is a two-armed robot that rotates at two joints to move the end joint to a desired position. Joint 1, denoted by the O in this picture, rotates the arm. Joint 1 has X and Y coordinates of 0, 0. The angle of joint 1 is denoted by theta 1. Joint 2, denoted by a capital A in this picture, also rotates. Joint 2 has coordinates x1, y1. Angle of joint 2 is theta 2. The end joint, which we typically call the end effector, is denoted by x2 and y2. This is where the tool will go. We created a Python program that the user can determine where on the plane joint 2 and the end effector will be. The program also asks for arm length, denoted by L1 and L2. The program then creates a graph plot showing the calculated arm position. We will compare the program to real-life measurements. Here is our crude model made out of Legos. The pic shows test 1. For test 1, measured values were as follows. Joint 1 measured 0 degrees with x coordinate equal to 98 millimeters, y coordinate equal to 0. Joint 2 measured 90 degrees with x coordinate at 98 millimeters and y coordinate at 31.3 millimeters. You can kind of see the end effector as well, that little yellow nub. So we are going to compare the measured values to our Python program output. Here is our Python program output. The red line is arm1 and the blue line is arm2. As we can see, just eyeballing it, we can see the red line is at 0 degrees, while the blue line is at 90 degrees relative to the graph. Here is our Python program output. The program asks for the length of arms, which we measured the first one to be 98 and the second one to be 31.30. Program asks for joint angles. Joint 1 is theta 1, which we put 0 degrees. Joint 2 is theta 2, which we put 90 degrees. The XY output is calculated as shown. This matches our measured values. Here's test number 2. Measured theta 1 was 90 degrees. Measured theta 2 was 180 degrees. Measured joint 1 coordinates was x at 0, y at 98 millimeters. Measured joint 2 coordinates was x at negative 31.30 millimeters and y at 98 millimeters. Here's test 2 graph. Looks pretty spot on. Here's program graph output. As we can see, it looks pretty spot on according to our measurements. Here is simulation output. All coordinates match our measurements except x1 at joint 1. x1 was measured to be 0 millimeters, but the output is at 6. I'm not fully sure why, but I would guess it's a compounding rounding error when converting radians to degrees within the program. It uses the math.radians function and math.degrees function. Here's test 3. Theta 1 was measured at 180 degrees, while theta 2 was 270 degrees. Joint 1 was measured at negative 98 millimeters for x and 0 millimeters for y. Joint 2 was measured at negative 98 millimeters for x and negative 31.30 millimeters for y. Here's test 3 graph. Again, looks pretty good. Seems to check out with our real life representation. Here is program output. Like test 2, all values match our measured values except joint 1 at the y1 coordinate. Again, I think this is just another compounding rounding issue. Y1 was supposed to be 0 millimeters. Here's test 4 setup. Test 4 was measured with theta 1 and theta 2 at 65 degrees. Joint 1 was measured with x at 48.52 millimeters and y at 86.40 millimeters. Joint 2 was measured with x at 63.78 millimeters and y at 113 millimeters. Here's test 4 graph. Looks pretty legit. Test 4 output significantly varied from our measured values. Variation deviation is shown on the right pane. Variation ranged all the way up to 9.14 millimeters. It's unknown what caused such significant variation. I would guess that it's a multitude of factors. For one, we did not have a precise way to measure angles on the real-life model. The model was not constructed for precise measuring of angles. Also, the standard compounding rounding errors probably plays a role in it too. That's all I got. Thanks for watching.